Here are some general questions with worked examples, so be sure to work through each question first before checking for the solution. So the first question asks us to find out what the angular velocity of a merry-go-round is. And in the second part we're asked to calculate how the speed of the horses vary from the inside to the outside radius. So remember that the thing that links the two is the angular velocity. What we want to find at both those points is the linear velocity. So I want to find the angular velocity, so I'm going to use omega is 2 pi over t, because I have the time period here of 15 seconds. So that is 2 pi over 15, and so the angular velocity is 0.42 radians per second. For the second part, there are two ways I can look at this. We could start off by saying that V on the inside is R on the inside times omega, remembering that omega is the same. And so if I put in the numbers, that gives me 5 times, so the inside radius is 5 meters, 5 times 0.42 radians per second, which is 2.1 meters per second. I can do the same on the outside, so V out is R out times omega, so that's 10 meters times 0.42 radians per second. I'm not putting the units in here, which comes out at 4.2 meters per second. So we can see then that if we go back to the original question, how does the speed of the horses vary from the inside to the outside, we can see that the speed on the outside is double. So we need to make sure that we answer the actual questions. The speed at the outside is twice that, or 2 times that. Of the inside. Another way to look at this is to look at our original equation. So we've got the speed on the outside, the linear velocity, is going to be equal to the radius on the outside, multiplied by the angular velocity. And the same for the inside. Now, if we form a ratio of these, so if we say that V on the outside divided by V on the inside is R on the outside divided by R on the inside, you can see that when we divide one by the other that the omegas cancel out. So this is what we want. We want to know what's the ratio of the speeds from the outside to the inside, and so if we simply put the radii in, so R on the outside is 10 meters, R on the inside is 5 meters, so that tells us that the ratio of the speeds is 2. So that tells us that the speed on the outside is twice that of speed on the inside. So we'll just rearrange that, put VI over here if we wanted to. Alright, for the second question, we've got a DVD spinning at 650 revolutions per minute. So we want to find what the speed is at a point 3.5 centimeters from the center of the disc. So first of all, we want to find the angular velocity in radians per second. So we know that the angular velocity is 2 pi over t, and we know here that the time period is 1 minute. So we want 2 pi over 60 seconds, 2 pi radians over 60 seconds. However, we have 650 complete revolutions per minute, so that means that we need 650 times 2 pi radians over 60 seconds, which gives us 68.1, so 68 radians per second. For the second part of the question, we want to know the linear speed, because we know that that varies according to the radius. So V is r omega. Our radius here is 3.5 centimeters, so you can write that for simplicity as 3.5 times 10 to the 2 meters, or you could type that in as 0.035 meters. It doesn't really matter. So 3.5 times 10 to the minus 2 meters times 68 radians per second gives us 2.4 meters per second. So our speed at a point of 3.5 centimeters from the center of the disk, remembering that linear speed is determined by the radius and the angular speed, which doesn't change, and so our speed at that point is 2.4 meters per second. This one's a past paper exam question, and you can see that it's all about a dust particle at position D rotating on a vinyl disc. And we're told that a combination of electrostatic and frictional forces act to keep it in the same position. So the first part of the question, as you can see there are 3 parts. The first part of the question is to calculate the linear speed of the dust particle at D. So there are obviously a couple of ways of doing this, but what we want to know is what r is. So r is 0.125 meters. That's the radius from the center of the disk. And we know that the speed of rotation is 45 revolutions per minute. So let's perform this calculation now. So using the information we were given before, we know that r is 0.125 meters, and we've got it's revolving at 45 revolutions per minute. So we could use the method we used in the previous question. We can say that the angular speed is 45 revolutions times omega over t, where the time period is 60 seconds because it's per minute. So that's 2 pi radians over 60 seconds. If we calculate that out, that gives us 4.7 or 4.71 radians per second. Of course, in any of these sorts of questions, you don't have to solve for the angular velocity. You could solve for the linear velocity directly by remembering that the linear velocity is 2 pi r over the time period, and here, which is the time for 1 revolution, in here we have in 60 seconds we have 45 revolutions. So it's perfectly acceptable to calculate the linear speed directly. I just want to show you a range of options. So the next part of the question asks us to mark on the diagram an arrow to show the direction of the resultant horizontal force on the dust particle. Well, we know it must be acting towards the center of the disk because it's providing the centripetal force, and you can draw a straight line acting towards the center of the disk. The next part asks us to calculate the centripetal acceleration at position B, so we can use the expression A is omega squared r. So before we found that omega squared was 4.71 radians per second and r was 0.125 meters. And so the acceleration then is 2.77 meters per second squared, or 2.8 meters per second squared. Of course, as an alternative, if you calculated the linear velocity in the other parts, then you can also use that the acceleration is v squared upon r and still come out at the same answer. For part C of the question, we need to explain why there seems to be more dust concentrated on the inner part of the disk than the outer part of the disk. And so we need to make use, first of all, in answering a question like this, on a relevant equation. And so one approach would be to say that if we start with that the centripetal force is omega squared r, then for a constant omega, the force is proportional to the radius for a given mass. So that tells us that we need a smaller centripetal force is needed for the particles on the inside. And so the fact that we have more dust particles concentrated in the centre tells us that the friction or electrostatic force must be great enough at that point in order to keep the particles where they are, because the force is large enough. However, the further away we are from the centre, then the force needs to be larger, and so obviously the force being provided by the friction is insufficient. As this is an exam question, I've pasted in relevant points required for the answer, as we've just outlined. And also notice that if you used earlier F is mv squared upon r, then you might have a little bit of difficulty answering this question at first glance because of the fact that both v and r change with the radius, and of course you can link these together using omega, and then obviously make the point that the centripetal force required is proportional to the radius when we have a constant angular speed. So you do need that to make that connection for this question.